Welcome, ladies and gentlemen, to your video lesson for 3.1. Hopefully you find this useful and informative, and it's supplementing your understanding of graphing relationships. That's what 3.1 is all about, graphing relationships. So we're going to start here with a bit of a warm-up. It says, tell whether the graph represents an increasing or decreasing relationship. Also decide whether or not the graph goes through the origin, okay? So for graph number one, we first have to break it down to like the simplest idea about how we read a graph. So we read graphs from left to right, just like you read a book, okay? So if I look at what this line does as I go from left to right, I would say that this is increasing, okay? And does the graph go through the origin? Well, the origin is the coordinate point 0, 0, right in the middle there, and it does not, so we would say no. Okay, looking at the next graph here, again, reading it from left to right. Is this graph increasing or decreasing as I look? The graph goes down as I go from left to right. So I would say that this is decreasing. And does it go through the origin? The origin, again, is that point 0, 0, and it does go through the origin. So I would say yes, it does. Okay, so just kind of a brief overview about reading graphs from left to right. Where is the origin? Things like that. Okay, so graphing relationships is what our focus is today. So a couple of things we're going to focus on are the ideas of number one, how do we read a graph and how do we interpret the meaning of a line going up or down? Also today, we are going to focus on domain and range, which are fancy words for X and Y values. And we're also going to focus on graphs that are continuous and discrete. So those four things are going to be our major topics in this video and on your lesson. All right. So we have a graph here that we have to interpret the meaning, okay? So the delivery van is a delivery van is from the warehouse varies throughout the day. The graph shows the distance from the warehouse from 8 o'clock in the morning till 5 o'clock at night. So on our x-axis here, we have time in hours. This would represent that 8 a.m. time, and this would represent that 5 p.m. time. And in between, we have distance that is measured on the y-axis, right? And as the van travels, we have different measurements of distance. So say this could be maybe 40 miles or whatever. We don't have any numbers here, but that's what's given an example, okay? So I have some examples here. I want to know what happens in segment number one. What happens in segment one, number one right here? Well, I'm noticing that this line goes up, and if this measures distance, then it started at the warehouse, and then after segment one was over, we are some distance away. So what I said is that we have the van leaving the warehouse, and that's kind of a steep line, right? So I would say that it's actually leaving fairly fast. So the van is leaving the warehouse fairly fast. All right, in the third segment, which is this segment right here, this flat piece, well, during that segment, during that time period, which is from, this time to this time, those aren't very good lines, but we're talking about that, right? During that time period, there is no change, okay? We can't say he got closer because it doesn't go down, right? The distance doesn't change. So I would say that, the driver is not going any farther from the warehouse, or maybe he's possibly stopped, right? It is possible that he's going in an arc around the warehouse. That's highly unlikely, though. So it's probably more likely that the van is stopped. Okay, segment number 5. Okay, so same as segment 3. So if we said segment 3 is stopped, then segment 5 is also stopped. But we could also say that it's the farthest that van will be from the warehouse because there is no point above that, right? He's maybe reached his farthest point out on his delivery cycle, and now he's maybe going to start his return. All right, segment 6. Segment 6 is right here, okay? And that goes downhill as far as reading the graph from left to right. And that distance goes from a large number at the start of this point to a smaller number, right? So the distance is getting smaller, which means that the van is starting to get closer to the warehouse. Then finally, segment 9, this segment right here, is very similar to segment 1, except for it's doing the opposite thing. And we could say a couple things, that it's returning to the warehouse. The van returns to the warehouse, and it's actually going very quick, right? Compared to segment 2, it's driving slow, okay? Segment 9 is very fast, like segment 1. But at the end of segment 9, the distance is 0, right? So it is at the warehouse. It is fully returned. And that's how we can use this graph to kind of interpret, like, all right, well, where's the van at a certain given time? I could also say, like, all right, well, where's the van at noon, right? Well, you need to look at the graph at noon. You'd say, well, it's at segment 5, and it's not moving at all. He's eating lunch. It's not moving. Okay? So an example of how to read a graph. Here are some more examples of how to read a graph. We have a scenario here that is graphed in 3 different ways. So the three hoses fill 3 different water barrels represented by the graphs. Okay, so we got water in gallons on each of the y axis, and we have time on the x. So over time, this is the water level being measured. Okay, so what we want to do is kind of match these. Okay, so the green hose, it fills at a constant rate. Okay, fills at a constant rate. Well, if I want to pick out what graph matches this situation, well, if I look at graph A, graph is kind of filling up slow here, and at the end, it's like filling up really fast. Okay, and here it's the opposite of that. So this would be graph B, because that time, the amount of the rate of the water going in there does not change. It's filling at a constant rate. It's not like really slow at the beginning and really fast, or really fast and then really slow. It's constant rate. Graph B. Black hose, slowly opening, and then it's completely open. Okay, so it's like that turning the dial right on your hose. Right, it's slowly opening. Right, it's not really coming out, and then you open it all the way. That's going to be first graph. Right, the water is slowly going into the barrel, and then towards the end, it's going in very fast. So that's going to be graph A. And then by default, that leaves it with C. But let's make sure it makes sense. Okay, so if I'm going to interpret this graph and be like, wow, it was really filling fast, and then towards the end, it kind of tapered off a little bit. And C says completely open at the beginning and slowly closing. So that does make sense with the graph C. Okay, another example of this, graphs of you and a friend playing catch. So again, we got graph A, B, and C. We got to match it with the description. So first, the first ball that you throw is in an arc and your friend catches it. So I throw the ball and my friend catches it. Well, I look at this graph, this is the height, right, over time in seconds. Well, that means it started at probably where, like, I can even draw a stick figure here. Be like, all right, dude threw the ball, right? Now it's going this direction and it probably is on the ground, right? Because I'm standing on the ground. This is on the ground. This one looks like it starts in somebody's hand, right? And then goes to somebody else. So there's my artistic drawing. And that's going to be graph B, right? In an arc, and your best friend catches it. There we go. Second graph is ball's in an arc and it gets stuck in a tree. Okay, that means that somebody threw it, right? And we got a tree, whatever. I'm drawing a tree, I guess. That's right here. That's going to be graph C. It goes up a little bit, but it never comes back down. So that's going to be graph C, and which leaves us to say that graph A is this last scenario, but let's make sure it makes sense. So third ball, I throw directly at my friend, but lands at his foot and rolls to them. So that's going to be this one, right? Throws it, lands on the ground, and then rolls the rest of the way where your other friend's standing. And so that's graph A. So again, making sense of how we can look at graphs over time. All right, some vocabulary. So this is going to be very important stuff that we need to know. So a continuous graph is a graph that is made of connected lines or curves. So a continuous graph has no gaps, okay? So that blue line that I drew with the arrow on it would be continuous because there are no gaps in it, okay? A discrete graph is made up of distinct, unconnected points. So this could be a discrete graph. I have discrete, individual, unconnected points, okay? And there are times where we have to graph situations where it wouldn't make sense to use a discrete graph or it wouldn't make sense to use a continuous graph, right? Then the other thing, so these are basically the 4 things I said we need to get out of today's lesson. Domain is the set of values for x, so all of the x values. So basically, if you took this graph here and made a table, it'd be all the x values, right? And then the range is the set of all the y values. And we write them differently for continuous and discrete graphs. So that's another thing that we got to learn today. Not only what domain and range is, but how to write them correctly for discrete and continuous graphs. Excuse me. All right, so let's dig in this. So the student takes a test. There are 10 problems on the test. For each problem the student answers correctly, he is receiving 10 points. All right, so the first question is this situation a discrete or continuous situation? Okay. Obviously, we got the graph here, and we said that discrete graphs are unconnected points, right? So these are unconnected points, so this is clearly discrete. But why does that make sense? Well, it makes sense because he's getting 10 points for every problem I get right. That means I can't get, like, if this is one question right, that is 10 points there. I can't answer half a question, right? And get 5 points. It doesn't exist. That doesn't happen. So because it's not something that actually can happen, I can't put it on the graph. So that's why a discrete graph makes the most sense here. The situation calls for it. Now, when we write a discrete graph domain and range, we literally list out every single number that could be an x value. Okay. So one of the things you can do is look at this and say, all right, well, what are my x values? Well, this coordinate point is 0, 0, right? This coordinate point is 1, 10. This coordinate point is 2, 20, and so forth, right? So then you can just pick out all of your x values, okay? So my x values so far are 0, 1, 2. And if you notice, it's a pattern, right? The x value here would be 3, and then 4, and then 5. And what I'm doing on the graph here is more visually probably quicker than what I was doing with listing out coordinate points. So all those lines I drew correspond to coordinate points. So my domain values are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, when we write domain, notice I have a capital D for domain, a colon, and then an open bracket, okay? Inside that bracket, we write x equals, and we literally write out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And those are all of my domain values. I could also do this in a shortcut and say, all right, my domain is x is equal to, and then it's equal to values 1, 2, 3, and then dot, dot, dot. That 1, 2, 3 means I've established a counting pattern, which means the next one's going to be 4, 5, 6, 7, 8, 9. But it doesn't go all the way to infinity, so I have to say where it ends. Okay? So this is a shorter way to write the same idea. Now, for the range, I use that same exact thought, but I got to think it's for the y, right? So let me erase kind of this stuff here and think about what my range is going to be. Well, my range, again, is my y values here, and those values are going to be 10, 20, 30, 40, and you guessed it, it's going to be all the way up to 100, right? So again, I could do y equals now, and then 10, 20, 30, 40, 50, 60, 60, 70, 80, 90, get rid of this, 100. Or I can write the shorthand version and say, all right, my range is equal to y, and all the values that can be y are 10, 20, 30, and then dot, 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 establish the pattern. And where does that pattern end? It ends at 100. That is a way that you could also write that in shorthand. Okay, so again, this graph was discrete because it had unconnected points. When we write discrete domain and range, we physically have to write out all the values unless there is a pattern, and then we can take advantage of that pattern and do it in a shortcut way. All right, so take a look at this one. Local businessman is going door to door trying to sell vacuums. For every vacuum he sells, he makes 20 bucks. He can sell a maximum of 10 vacuums per day. So this is a graph, and on the graph I got values 2, 4, 6, 8, 10. Really, it's 1 through 10. And up to 10 is the number of vacuums. So this just must be one day, right? One day of sales. Okay. And first question I want to ask is, before we even graph, okay, is this continuous or discrete? Well, question then becomes like, can you do a partial thing, right? Before we're like, well, can I answer half a question? And the answer is no. So the question here is like, well, can I sell a half a vacuum and make $10 or a tenth of a vacuum and make $5? No, I can't, right? Or $2. I can't do that, right? So for that reason, this is also a discrete graph, okay? Now, if I sell one vacuum, I get $20. If I sell two vacuums, I get $40. So this graph looks like what you see here now. 1 and 20, 2 and 40. And then the domain, remember, we have to write the domain every single value, okay? So remember, we start with the D colon, open bracket, X equals, and then we listed all the values. 0, 1, vacuum, 2 vacuums, but 3 vacuums. And then I took advantage of the pattern here, right? And said, all right, I'm going to stop at 10. So I could have listed 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but I took advantage of the pattern and I stopped at 10 with it. The range, again, is the same way, but this range is not, 1, 2, 3, 4, right? You think about what it is. So the R is a range, bracket, colon, then bracket. Then you have to put Y equals, okay? And then if I sell 0 vacuums, I have $0. So 0 is part of that, right? If I sell 1 vacuum, that's $20, and then 2 vacuums, that's 40. So my range looks like so. But it goes all the way up to 200. So again, I took advantage of the pattern here to make it a little bit shorter. So again, discrete graphs are unconnected points. And when you write your domain and range, we only write individual values, and we can take advantage of the pattern if we need to. All right, so a bathtub is being filled with water. After 10 minutes, there are 75 quarts of water in the tub, and somebody accidentally pulls the plug, and while the water is still running, the tub runs to empty. The tub loses 15 quarts in 5 minutes, and then someone plugs the drain, and the tub fills for 6 more minutes. After gaining another 45 quarts of water, After a 15-minute bath, the person gets out, puts in the drain plug. It takes 11 minutes for the tub to drain. Let's just say tub, not tube. All right, so we have a whole bunch of details here, which we're going to go back and gather up. But basically, this is a situation where, we have water in a tub. Okay. Now think about if this was going to be discrete, right? What that means is that somehow miraculously we would go from no water in the tub, and then you'd blink an eye, and then there'd be 3 inches of water in the tub. Or in this case, it would be 75 quarts. Okay. So that doesn't exist. That's like magic. That doesn't happen, right? It fills up over time. So for that reason, this is a continuous graph because, after 30 seconds, I can have just part of a quart of water in there. And that makes sense. After just a tenth of a second, I can have a little bit of water. So all of those values in between now make sense and are possible. So therefore, it is discrete. Okay. So my domain for this, right, are all the possible X values. Okay, all the possible X values. So the problem with writing all of the X values out is that, well, I don't know. I can't physically list them all, right? Because, 10 minutes works, right? But 11 minutes works, and 11 minutes and 30 seconds works, and 11.6 minutes works, and 11.000. What you should be understanding is that it's not possible for you to physically write them all out. In a continuous graph, that is the case, okay? So what we have to do is write an inequality. An inequality covers every single value. Now, when we write an inequality, go back to what we talked about last lesson, right? Our values for X go from 0 to, it's like 47 minutes here. Okay. And if it goes from 0 to 47 minutes, then we have to include all that time in between. So what we say is that the value of X is going to be less than or equal to that 47 minutes, okay? But it's got to be greater than or equal to 0 minutes, right? Because there is a time 0 where there is no water in the tub, okay? So that would be our domain here, okay? So if we're keeping track of water in the tub, let's just kind of go back to the details of this. So the bathtub is being filled with water, okay? And being filled with water, and after 10 minutes, there are 75 quarts in the tub. So this is 75 quarts. I'm just kind of keeping track. Then someone accidentally pulls a drain plug while the water is still running, and the tub begins to empty. The tub loses 15 quarts. So 75 minus 15, we go down to 60 quarts here, okay? And then someone plugs the drain and the tub fills for 6 more minutes, gaining another 45 quarts. So we have 60 and then plus 45 going up this part here, right? Which gives us a total of 105 quarts. And I did that because I wanted to know what the maximum amount of water was in the tub. It's 105. Okay. So now when we write the range here, again, it's not possible for me to put like 1/10 of a quart, 2/10 of a quart. It's ridiculous, right? I'm going to write another inequality. It says that y has to be less than or equal to maximum amount of water, which we said was 105 quarts. But then also it's going to be greater than or equal to that zero value, right? At times zero, right? At time zero, there was 0 water in the tub. Okay, that's an example of a continuous or discrete graph. That one was continuous. Okay, another one. At the start of a snowstorm, it snowed 2 inches an hour for 2 hours. So think about this before I even go any further. We're going to have to answer the question, is this continuous or discrete? Just think of how ridiculous it would be for a snowstorm to be discrete. Probably be dangerous, right? So all of a sudden you snap your fingers and boom, 2 inches of snow just right now falls on the ground. You probably have a whole lot of broken necks for people walking around outside. So right away, I'm going to say that a snowstorm is not not discrete. It is a continuous situation. It snowed 2 inches an hour for 2 hours. Then it slowed to 1 inch an hour for an additional hour before stopping. 3 hours after the snow stopped, it began to melt at 1/2 inch an hour for 2 hours. Okay, so the details of that graph are pretty clear that it's continuous, which means we're going to have to write some type of compound inequality, right, for x and for y. So the graph for this would look like so, okay? So the maximum amount of inches of snow that we had, if you go back and want to match up the details, the maximum amount of inches of snow that we have is y, and the maximum time that it takes here, we kind of keep track because we want to know, okay? It snowed for 2 inches for 2 hours, right? 2 inches, so we got 2 hours there, right? Then it snowed 1 inch for an hour for an additional hour before stopping. So that's there 3 hours. And it didn't do anything for 3 hours. And it began to help for another 2 hours, right? So from 6 to 2 hours after that, we go up to 8. Okay. All right. What that means is that my time for the snowstorm goes from 0 to 8. Okay. And it includes both of those times. So there is my domain for time, right? It starts at time 0, and my value of time has to be greater than time 0, but it stopped after 8 hours, so it has to be less than or equal to 8 hours. And then my snowstorm, the total amount of inches was 5 inches, right? And in between that, I have all of the measurements between 0 and 5 inches of snow. And so the range for y has to be less than or equal to 5, because that's 5 is the maximum, and then greater than or equal to 0. Okay. That is a continuous example with the range and the domain, showing how you have to use compound inequalities to say what that is. All right. So the 4 things, like I said, for today's class, what you should have gotten out of it is that you should have been able to understand what a discrete and a continuous graph is. And then for each of those, right, for a discrete graph, remember we write domain and range by listing all of the x values. Sometimes you can take a shortcut. And then for continuous graphs, we have to write an inequality for the domain and range because it's not possible to write all of them because all of the numbers are included in between the ones that we're talking about. Okay? Those are the things you should have gotten out of today's lessons. I hope that you're having a great day. Peace.